today we're going to look at the P version of the finite element method in higher dimensions. And we're going to look at functions for quads, and perhaps I'm going to show you a little bit about triangles too, because you can also do this with triangles. So usually when you're trying to mesh a geometry, meshing that geometry with quads is straightforward as long as your domain is regular, but you can get into some issues, so triangles are actually better for that purpose, for arbitrary geometries. So say you have a quadrangular element, and we have worked with isoparametric formulation so far. So now we have similar idea. So we have this is our master element for a quad. Let's number the nodes 1, 2, 3, 4 like this. Yeah, and the coordinates in 2D are going to be psi eta, and this is going to map to physical space to some configuration that we are going to, let's make it arbitrary. And of course the numbering here could be anything, because we're actually talking about the nodes of the mesh. And let's say this is our element, and this is our node 10, 11, 30, 31. Those are the node numbers. Now, because of the mapping, as we discussed a few minutes ago, it really doesn't matter. I mean, in physical space, you don't have to really order the nodes in a particular way, as long as you are consistent and you're always ordering the nodes counterclockwise. So for this case, numbering the nodes 10, 11, 30, 31 is okay. And numbering them 30, 31, 10, 11 is also okay. So you have to be just numbering counterclockwise the nodes. Of course, the correspondence of those nodes with those of the master element are different, but that doesn't matter because everything is taken care of automatically by the mapping. Okay? So now this, we're talking about some physical coordinates here just to complete the figure xy. So now we have to define some shape functions, and remember that we did p-FEM in 1D, and if you remember, we look at some very particular types of functions that had a very nice property. What were those functions and why we use those functions?
Legendre polynomials?
We use Legendre polynomials because they were different. They are different. But what was the nice property about Legendre polynomials? They were different from each other. In other words, they were orthogonal to one another, right? And that had a very nice property because it didn't degrade the condition number as we went up in polynomial order. So it's a really nice choice for p-FEM. So we're going to do the same, but before we get into that, we're going to talk a little bit about the spaces that are used in p-FEM, right? And there are normally two spaces that people use, and I will discuss a little bit about that too. So now, we also looked at the geometry. Remember that in h-FEM, we're using an isoparametric formulation. When we moved to p-FEM, what type of formulation we were using? It was no longer isoparametric. It was subparametric because our geometry, our field was interpolated with higher order polynomials, but our geometry remained linear, right? That's why when our geometry is interpolated with less degree than our field, then the formulation is subparametric. Okay, and the same is going to happen here because we're going to rank up the polynomial order for these quads, and we really don't want to do the same with the geometry, unless of course there is a reason to do so, right? So we are going to talk a little bit also about the types of geometric mappings that you can have. But before that, as I said, let's talk about the spaces that you use for p-FEM. Okay, just to complete here, I'm going to say this is subparametric. We're going to use subparametric. And there are normally two spaces that people use with p-FEM. One is called the trunk space. And we're going to call this, we're going to denote the trunk space with this symbol. So S denotes the space, TS because trunk space, and then P is the polynomial order that we want. And this space is spanned by the following monomials. And keep in mind that now we're talking about spaces, right? Function spaces. So we are not yet talking about the actual shapes that we're going to use, our shape functions. We're not working on those yet. But let's say the terms that are going to be forming our approximation, right? This is what is defining the space. And the monomials that are used here are psi to the power of I, eta to the power of I, and for I, j equals 0, 1, and so on, p, I plus j is equal to 0, 1, all the way to p. And we're going to use psi eta if p is equal to 1. And also psi to the power of p eta and psi eta to the power of p for p greater than 2. So let me I'm also going to do the not disturb here. Okay. So if you look at the Pascal triangle, so for p equals 1, let's say this is my then for p equals 1, I'm taking basically into account only these terms. So there are 4 terms. And you can immediately see that we basically recover the space that is used in a standard FEM because our quadrangular finite elements in HFEM, these are called the bilinear elements, right? And it's called the bilinear elements because we have that term, right? Now for p equals 2, where am I going to put this? Let's see. For p equals 2, of course, we have the same monomials as for p equals 1. Remember that we have, every time we are talking about polynomial spaces, we want them to be complete. So as we increase the polynomial order, we really want to keep everything that we had so far. So if you go from p equals 2 to p equals 3, we need the linear and the quadratic as well, right? So for p equals 2, then the Pascal triangle would look like this. And then those are the different terms. So this is one of the spaces that are used when people work with p-FEM. It's called the trunk space. And I'll show you a little bit more about this in a minute. I'm going to copy an image. The other one is called the tensor product space. And we're going to denote this by S, PS, and then I'm going to put here p psi comma p eta, because the interesting feature about this space is that you can actually choose whether you want to have a high order polynomial in only one direction, right? Before, let's say our trunk space was in a way symmetric in the way we are introducing all these terms into the approximation. In the tensor product space, we have more freedom, and we can say, well, let's just use a high order in the x direction, because who knows, maybe there is a steeper gradient in the x direction that you want to capture better, right? And in the y direction, you don't want to do that. You want to remain, let's say, quadratic or linear, and so you have the freedom in this tensor product space to do that. So this is spanned by a to the power j, and then I is equal to 0, 1 p psi, and j the same. So we're basically having the freedom to choose this independently. You don't have to keep the symmetry. Yeah. Let me see if I can actually grab one of those images from the book. This is the image I was looking for. Let's see. And here you have like the difference, how they look, right? So your tensor product space, I'm just showing as long as we keep the symmetry, this is the way they look. So you have the blue lines, and the other, the trunk space is shown. You see how it looks like, I don't know, like this strange plane that is invisible. Yeah, so those are the two spaces that we usually work with when we're talking about p-FEM. Yeah. Now let's talk a little bit about the shake functions, right? 13. Let's see. Missing something here. Okay. So between these two, what people use more, which one is your guess? Which one people use more between these two? Or did I say that already? Huh? Yeah, people use more the trunk space. So you can see basically as you go to higher order polynomials, you can see that the other space is really not being complete, right? So it's really neglecting the sides, and that's what the trunk space is trying to avoid. So in a way, the trunk space is more complete as you go high in polynomial interpolations. Now, of course, if there is a nice reason to provide a higher polynomial order in one direction than the other, then you can get to choose the other space. But let's talk about the shake functions now, because this is what we're really interested in. That is what we need to do to implement p-FEM. We need to talk about the shake functions. So okay, if we are looking at our element, you remember our bilinear quadrangular element. This is the bilinear element, so it's we already have shake functions for this element. Those are linear, right? What bilinear in this case. But if you remember p-FEM, what did we do in p-FEM? We basically had our linear functions, and on top of that we added high order shake functions, and they all had this nice property that they vanished at the vertices. So in a way, we were improving our approximation, going up in polynomial order, right, by hierarchically adding information into the space. That was a really nice feature. So for here, we are going to basically do the same, because our shape functions in 2D are going to look like, okay, we're going to keep the linear shape functions at the nodes, right? And then all the other shape functions are going to be such that they are going to vanish at some edges, or even at all edges, as we will see. So there are three types of shape functions for the quadrangular element. So we start with the nodal functions. So you have the nodal or vertex modes. And these are the same as standard FEM. Standard FEM, which as you know by now is also called h-FEM. So the shape functions are given by psi, comma, eta, and then we have 1, 4, I plus psi I, 1 plus eta I, where these psi I and eta I are the coordinates in master space of your node. So if we're taking, for example, the first node, if you remember how we designed our master element, well, if I look at the first node, my psi I is going to be -1, my eta I is going to be -1. So when you plug those into that equation, then you get the first shape function. So for the next one, psi I is going to be equal to 1, eta I -1, and so forth. Okay? So those are the first functions, and those are the same as standard FEM. So just to complete here, where of node master element. Okay, then we're going to have edge functions. Or side modes. Yeah, and we really want to have this because if we want to have, let's say, a high order interpolation in p-FEM, we're going to have conformity along edges, right? So let's say if our entire interpolation is quadratic, so there has to be some quadratic function that has to be shared along the edges of the elements. And of course, as you know, our linear functions cannot do that, so we have to provide an edge function that is quadratic along those sides. Okay? Well, it turns out that there are p-1 edge functions. And these are associated with each one of the edges. Yeah. And now I want to ask you, how would you construct a function, let's say, if we take a look at this element that we have here, what we want is basically to construct a function that is quadratic along that edge, and it basically vanishes in the other three edges. So who can tell me how can you construct a function like this? Yeah, so here we're basically, it's going to go down. Huh?
It's not just a simple quadratic in terms of eta or zeta.
Yeah, well, that's kind of what I'm looking for. So in one direction, you basically provide a quadratic function, and then in the other direction, what do you do?
Provide another quadratic function, but in terms of psi and eta.
Yeah, it's going in that direction. So we have one part here. So we construct a quadratic function in one direction. So you see that let's say let's go to master space. So if I want my quadratic function to look something like this, right? I would construct a quadratic function that behaves like that in the eta direction, and then in the psi direction, I need it basically to vanish at this other edge here. That's what I'm looking for. So then I would have, yeah, go ahead.
Lagrange. That's you use the second order.
No, but how will you do it? Let's say,
Is it so that you multiply a linear one with a
yes, that is the answer I was looking for. Nice. So you see that if you have a quadratic function in that direction, and then I multiply this function by a linear function that basically behaves something like this. Then you are basically eliminating that function at the other edge. That's exactly what I was looking for. And so that is exactly how these edge functions are built. It's 1, so this is the first edge. So that is the part that is basically eliminating the function at the other edge, right? And now we need a function that is quadratic in terms of psi. And who has an idea what functions are used for that? So this is the part that is taking care of, making sure that the variation is linear. So of course, right now I'm swapping the coordinates because I'm talking about the first edge. So the quadratic term is along the psi direction, okay? So along eta here, you see that is going to be equal to 0 when eta is equal to 1. So I'm talking about this edge that I have here. The first edge is this one, okay? So that term, 1/2 of 1 minus eta, when eta is equal to 1, that is going to be 0. So I know that along this edge, that is equal to 0, okay? And that whole thing along this edge is going to be, the bottom edge is going to be equal to 1, correct? But now I need to multiply that function with the one that is varying in the psi direction that we said that is going to be a quadratic. So what functions we use for that? Yeah, we use the same functions that we used before for the 1D case. And so we are going to use a function that we call, if you remember, phi hat. That is a function of psi, and of course this I, of course, it goes from 2 until the order that you want. And if you remember this function, there was something particular about the function, but it looked kind of like this. Two I minus 1, and then there was the recursive calls to the Legendre polynomial. So you could construct this by making the functions call themselves. But this was defined earlier for the 1D case. So we use the same because those are nice functions to work with p-FEM. So those are the edge modes. And now we need one more type of modes, and these are called the internal or bubble modes. And as you would expect, what is a nice property about these modes? Who can tell me a nice property about this? Think about a shake function that only acts in the element. Lot of silence. So for the other space, we have p psi minus 1, p eta minus 1 for p. But the nice property that I was looking for is that the functions are such that they all vanish at the edges, because we have already functions that define the polynomial interpolation at the edges. So now these bubble functions are only acting inside the element, and they are vanishing along the edges completely. You have a question?
Yeah, what is the second word on the last line? D and then
For the case. Yeah. So those are all the functions, and let's see, let's just copy from here. Have a nice image. Uh-oh. Okay, apparently I cannot paste this image until I start a new page. That's okay. But you see, now we're talking about all the way up to p equals 5. Yeah?
I have a question, because you said this is 2D, but now we have a surface which is deforming in 3D. So how is this 2D?
So the element is two-dimensional. So I'm plotting the function as a function of x and y, or c eta in this case.
Okay.
Yeah, so you can see the first column here are the linear functions. So you see that the function it's equal to 1 at one vertex, and they go along those edges. They go linearly to 0, right? So you have 4 because you have 4 vertices, right? The second column are the ones that are quadratic on the edges, right? Then you have the cubic, and you see now that there is a little bit of a problem. Because who can tell me what is, let's say I'm putting 2 elements next to one another, and let's look at what's happening at the edges. What is happening at the edges? If you look at the even functions, like the ones that have p equals 2, 4, 6, those are not the problem, but the problems are the ones that are even, the odd functions. So the even functions are fine, but the odd functions have an issue there. What is the issue? That is a problem. That is a problem. Can you tell to everybody what is the problem?
I'll try.
Yeah.
If you look at the first image of at p equals 3, at the left side it goes downwards.
Yeah.
And then you could have a node next to it where it would go upwards. So
Yeah.
you create this continuum.
Exactly, and that is a problem, a big problem in p-FEM. The fact that when you basically put 2 elements one next to one another, right? These odd-shaped functions basically become non-conforming. So you can end up with a non-conforming discretization. I think we're late. I'm going to take a break in a minute. You understand? So there is a trick to fix this, but this is the only issue that you have to be very careful, because the moment let's say your odd functions do not agree along the edge, then you get all sorts of issues, and it's really hard to track. This is the type of bugs that are really hard to track. Yeah.
Why is this not a problem for example, p equals 2?
Yeah, because for p equals 2, they agree, so it's still a conforming discretization. The problem is that they are the even shape functions are symmetric along the edge, right? But the odd shape functions are not symmetric.
How do you mean along the edge? Because
Okay, what let's see if I can. I'm gonna try to draw what is the problem here. Let's say you have one element like this, and then you put another element next to it. So if you look at an odd shape function from this element, it's going to look something like this. Now, if you take a look at the odd shape functions from the other side, it's going to look like this. And now you have functions that are not matching. And so the associated degree of freedom to that function, right, is doing something strange because you have a behavior that is really not conforming. So it's the same thing as you have in standard FEM when you have a hanging node, where you basically can have it's called a non-conforming discretization, right? So your solution may become discontinuous. Well, here's the same. You see, the shape functions are not paired in a way, right? So you can have a non-conforming discretization also in p-FEM because of this issue. So that is the only thing we have to take care about. So I'm going to write that real quick, and then we're going to go to a break before someone else stands up and go to the break. So there is a really nice trick to avoid this, and the solution, or at least this is what we have implemented in our code, is just to use the normal to the connectivity in that element, right? If you have the nodes are numbered, let's say you have at that edge you have node 30, 31, right? And if you are considering that edge shake functions from the element that has 30, 31, then let's say 30 is less than 31, and so the normal is correct, right? And if you're considering that same edge on the other side, on the other element, it's going to be 31, 30, and because this is basically 31 is greater than 30, we call it this lexicographical order, then I just reverse the normal, and this is a nice trick that you can actually play when building these functions.
Is it also possible to skip all functions at all? Just use
Your solution is not going to be complete, and that may be a problem. So of course it is possible, but you are guaranteed you're not going to get the exponential rate of convergence. You always want to have a complete. You want to make sure that in your Pascal triangles all the terms are really represented. You don't want to miss some terms. So this is for ensuring continuity, okay? And just to really quick, I'm going to paste the ones for triangles, just to show you that you can also do this with triangles, not only quads. For the book, we are actually using Chebyshev polynomials for the triangle. So also to show you that you don't have to use Legendre, but any choice that is a nice polynomial basis is actually a good choice. So I'm going just to complete this image. I'm going to put the shake functions for triangles, and if you look, they actually look similarly, right? So you have the vertex modes, and then the quadratics are quadratical on the edge. The cubics are, again, they have the same issue. They are not symmetric, of course, as you would expect, and so you have to take care of the same issue. Okay, so well, that is basically everything I wanted to cover regarding p-FEM. We're going to talk a little bit later about the mapping. We wanted to keep it linear, and we're going to talk a bit about enforcing Dirichlet boundary conditions, which is the main issue here. So let's take a break. Let's see each other in 10 minutes.